And again, we start on up. In this case, we're going to jump right on into Lewis structure. And Lewis structure is a bit of a pet peeve, so be aware of this. What I would like you to go through and do is provide the Lewis structure for the complex ion sulfate, so SO4 - 2. For those of you who are like, but didn't you say we don't have to worry about sulfur? Yeah, Lewis structure, do it. Perhaps most important behind this is not just the structure for sulfate, right? Because what I'll very often get, particularly in an online system, you'd be like, well, I don't know how to do that, I'm just gonna look it up. You can't look up everything. It won't work. It literally will not work. You need to have some kind of understanding of how to draw these things. So it's not so much draw the structure for sulfate, it's what were the steps that you used to draw the structure for sulfate? And that's kind of the crux of Lewis structure. And it's the steps that you're going through and how you're accounting for things that's going to become a really big deal moving into OChem 2 or even later in this semester. So spend a hot second to try and figure that out. That means pause. Spacebar works. You can click the little 2-line things. It works as well. And pause it, come up with a system. Now that you've come up with a system, there's a couple things that I'd like you to do with this. Number one, post your system to the discussion board. So let's see what everybody thinks about Lewis structures and how you should go through and do it. One of the things we'll probably see is that no one's going to post. And why? You're all like, I don't know what the rules were. My rules kind of sucked. How do I put this nicely? They did suck. Okay, and that was nice. That's not necessarily your fault. And it's not really your Gen Chem instructor's fault either. One of the problems with Lewis structure is that you don't practice it in Gen Chem. It becomes a one-off system that you just race through in Gen Chem, and so you get Gen Chem instructors building rules and the internet building rules that allow you to draw the structures quickly while cheating an understanding of the knowledge, okay, of what's going on behind the structures. That's all fine and dandy in Gen Chem when you don't have to apply the structure. OChem, you have to apply the structure, which means if you're using crappy rules, you're going to get crappy structures, which means you're going to get crappy grades in OChem. So make sure you understand your rules. For those of you who are like, nah, my rules are awesome, I don't believe you. So post your rules and then try and use somebody else's rules. So let's see where we're at with this as an overall class. This is anonymous, so you can post these as anonymous to our discussion board just to see what's out there, okay? And then use somebody else's rules to try and draw these things out, okay? We've got the phosphite ion, PO3 - 3, and CHO+, okay, as a cation. Okay, I don't even know how to name that, so I'm not going to worry about it. Okay, so we want to try and attempt these things. What we will see later on is that I do have a rule set behind this, and my rule set does look very cumbersome, and I'm aware of that, but the cumbersomeness of my rules, there's an underlying meaning behind each of them as to why we do them. Okay, so if we started off, we want to know how many electrons need to go into our drawing. So if we picked something like sulfate, we would have to address the electrons from sulfur, valence electrons. So we could look at our periodic table, see that the group it's in is the 16th group or group VI. Either way, we get 6. Oxygen, there's 6, but there's 4 of them. And then when we look at the charge, we're looking at an extra 2 electrons. We know there's an extra 2 because it is a negative sign. So we would be adding 2. So in this case, what we're doing is totaling up our valence electrons. And if we total this out, 24 and 6, 32. 24 and 6 for the record is not 32, it's 30, plus 2 gets us 32. The center atom, okay? The center atom should be sulfur. I'll get a lot of people saying, oh, it's the first one that shows up. In a simple Lewis structure, yes. Okay, but as we'll quickly see in OChem, we don't really have center atoms, which makes it a lot more difficult to do. But that center atom, the one that we typically find in the middle of our structure, or middle-ish, is the least electronegative, right? And it has to be the least electronegative because our electrons, if we have the center versus the outside, well, the center is in the middle. It's going to be required to share electrons. The outside may not have to share electrons. So we want the atom most willing to share electrons, lowest electronegativity, in the middle. That's why we do our placement. In this case, we're looking at a simple structure. So we'd be scattering our other elements around on the outside, okay, of that center atom. Again, if we don't have center atoms, that becomes trickier. We now need to place our electrons. And here's where the big difference comes into play from how I set this up versus how virtually anybody else does this. Our electrons don't get placed according to how many valence electrons are there. That's irrelevant. It's according to which element is the most electronegative. Well, oxygen being the most electronegative should have the electrons first, okay? And I'm going to place them in a way that I know eventually satisfies what I need to, which means I need to have a bond in here, which means, whoops, I'm going to start placing my electrons in that space. So I'm going to place 2 electrons there. Well, how many electrons should go around our atoms? For those of you saying, well, oxygen it's 6, sulfur it's 6, carbon is 4. No, you're wrong. It's the octet rule. There's a reason we have the octet rule. 8 electrons need to go around the oxygen. So I place 8. I'll go to the next oxygen and place 8. And the next oxygen and place 8. And I'll do this until I have satisfied all of my octet, or not my octets, until I have satisfied all of my electrons. So at this point, I now have 32 electrons in my drawing, 8 times 4. Okay? No extra electrons, so I don't need to worry about placing any around the sulfur. Now, anywhere I have a pair of electrons between atoms, I turn into a line. And you'll see some chemists go through and turn lines in for any pair of electrons. Well, the point of doing it only for atoms or electrons between atoms is to differentiate a bond versus not a bond. Easy way to tell. This also helps to reinforce that that line represents exactly 2 electrons. Okay? So great, we now have a structure. If we were in Chem 130, we would now verify octets. If we go through and look at this oxygen, how many electrons are around it? 1, 2, 3, 4, 5, 6, 7, 8. For those of you asking about that 7, 8, it has access to those electrons. That's the point of a bond. It's shared electrons. So there's 8 electrons around it. We could then go through and do this for each of the other atoms within this, and we would note that every single atom has an octet. Okay? So if it was a Chem 130, at least at Chandler-Gilbert, according to our Corwin textbook, we could put brackets and a -2 and be done with it. Okay? But this is not a Chem 130. This is ochem. And when we move to ochem, we can't just say that that charge applies to the molecule. We have to say that that charge applies to very specific atoms. We're placing the electrons according to the atoms, not towards the molecule. So now we have to go through and say, well, what are the charges on each of the atoms? So we have a new system that we have to account for. We have to look at what's known as formal charge. When we look at formal charge, there are a variety of formulas out there. Gen Chem uses one so that you have the same unit. I would argue the units are kind of irrelevant here, which is why I don't teach Gen Chem. Valence electrons for your individual atom, minus non-bonding electrons, minus the number of bonds. Note the unit difference. We're looking at bonds, not electrons there. So if I take a look at my first oxygen, oxygen comes in with 6 valence, minus non-bonding electrons, I see 6, minus 1 bond, it gets a -1. I like to put the negative symbol and circle it so that I don't get it confused for, say, a bond or just random dots. If we are careful, we should note that every single one of those oxygens has the exact same system associated with it, so they would all be negative. That should be a problem because now when we look at the overall molecule, it's a -4, and according to our symbol, our formula, it should be a -2. Well, it shouldn't be too much of a problem. That just means the sulfur has to be a +2. So let's verify that. Sulfur comes in with 6 electrons, minus 0 non-bonding electrons, minus the number of bonds, 4 plus 2. If you move to different rule sets, you may not be able to identify the individual charges in this structure because you would say, oh, the structure is wrong. The structure is not wrong, okay? It has different rules that we're following to get to it. So you have to make sure you understand those. Which then takes us to the next layer for ochem. In ochem, or perhaps in your 151 class, you may have been asked to push beyond this. This structure is exceptionally charged. And as you might have already guessed, charge is not particularly a good thing. For those of you being like, well, I didn't realize charge was a bad thing. I can't like gesture because of how our image is drawn, but there are these things called electrical outlets. And those electrical outlets where you're getting power so that you can see this has electricity in it. Those electricities are electrons, which are ultimately charge. Those electrical outlets are very, very dangerous if you plug the wrong thing into them, and you could get very, very hurt. Okay? That's because charge is bad. Okay? So charge is inherently high energy. Our molecules don't want to be charged and will so do whatever they can to minimize that charge. So when we're drawing this structure, every single atom has charge. That's bad. So what will happen is we will attempt to minimize that charge by moving electrons. I can take a pair of electrons and I can move it in such a way, shouldn't have picked that particular oxygen, I can move that pair of electrons so that the oxygen does not lose access to them, but the sulfur gains access to them. I now have an extra pair of electrons between the atoms. I can draw that as a line. If we go through to calculate formal charge, that oxygen is now no longer charged. I've reduced the charge in the structure. The sulfur will also come in now as a +1 charge. Cool, I'm minimizing charge. I can do this again with another pair of electrons from another oxygen. That other pair of electrons generates a new bond, and the formal charge on the sulfur now goes away entirely. What I've now done is exceeded the octet on the sulfur. Some elements are allowed to have octets exceeded. Okay? It is fairly rare, okay? But it can happen. And it typically only happens in a case where we could potentially put more electrons in, which means we have to have orbitals to place those electrons that are roughly the same energy. When does this happen? Third row. Third row elements have the ability to exceed octets. Anything lower than the third row, fourth, fifth, sixth, so on, can exceed octets. For this very reason, we have the ability to put more electrons in, largely due to those d orbitals being very close in energy. The second row elements like carbon, oxygen, nitrogen, all of those are so small that we don't have access to more orbitals, which means we can't place more electrons in, which means we don't exceed octets. Okay? That's the point behind these. So if we now look at our drawing, this drawing becomes a better drawing than the one we had before because we've now minimized charge. Yes, we've exceeded octet. That would generally seem to be a bad thing, but it's okay to exceed the octet as long as we have the ability to do so. Sulfur's in the third row, we have the ability to do so. And we now have a Lewis structure. For those people saying, well, I didn't draw that Lewis structure, what you're encountering is the next most challenging aspect within ochem, the concept of resonance. In resonance, what we're saying is that the electrons aren't forced into one location. They can exist across a larger spread of the molecule. If you immediately draw this structure with double bonds, you now lose access to your understanding of resonance because you don't see the reason for why a double bond was needed. The double bond was needed to satisfy or to minimize charge, or sometimes to satisfy octets. Resonance allows us to address that by shuttling those electrons around. Double bonds and triple bonds don't just exist, they exist for a reason, okay? To satisfy octets or to minimize charge. That's why they're there, not because I feel like drawing a double bond. Okay? That subtle change in understanding makes a big difference when it comes to manipulating how electrons move. That's what we see later on in the semester. For those of you saying we didn't draw that same structure, this is where resonance comes into play. I could have used any lone pair from any oxygen, which means I get multiple ways I could have drawn this structure. What does that also mean for us? If you were asked to draw the Lewis structure and this was the structure you drew, you get partial credit. Partial credit because you didn't address that there were other ways that those electrons could have been shown that did not change the overall energy of the molecule. Challenging concept, that's the point of what we'll be moving through when we look into resonance in a little bit more depth. So the next part behind this is we need to get an understanding of best Lewis versus useful Lewis. There are rules for assigning best. First rule, it's incredibly easy to forget, and we will forget it multiple times, and we'll talk about it in second semester also. Satisfy octets. For any Lewis structure, your best Lewis structure will have every octet satisfied. Every single one. Okay, so if you're drawing a structure where the octet is not satisfied, you're wrong. Okay. The next one, minimize charge. Okay. So you can rearrange those electrons into different bonds. Just make sure that you don't lose octets. You can exceed octets if and only if you are in that third row or lower. Okay. There are other cases that pop up, but those are the two primary examples. Okay. So best is what you typically see on a multiple choice exam. Useful, it's a trickier one. Useful is what you're going to use to try to predict how something's going to react. Okay? That best and useful we'll keep making reference to as we move through the semester, and we'll look at some structures that address this best versus useful. Sulfate's not a particularly good one to look at for best versus useful because sulfate is incredibly stable. All of that resonance stabilizes that charge, ultimately making it not reactive. So we would need to move to a structure that was reactive to get an idea of best versus useful. Okay? So rules, these are the rules we walked through. These are the rules you need to be addressing. Okay? Each of them has an underlying reason for why we're doing it. These rules become very important, and when we talk about, or I ask the question, well, how many electrons are around that atom? These are the rules we're using. If you're looking at it and saying something else, I will end up saying you're wrong because you aren't using these rules. If you use a different rule set, we have to make sure we're on the same wavelength. That means you and me individually, which isn't easy, particularly in an online system, okay, to make sure we're on the same wavelength so that I can help you get to the answer through what I would argue was a bad method. Okay? So make sure you understand these rules, and you should be drawing lots of Lewis structures. Okay? Typically, when we talk about an ochem class, they make you draw hundreds of Lewis structures. I would argue you don't need to draw hundreds of Lewis structures. You need to understand why you're drawing them. Once you understand why you're drawing them, you can do pretty much anything. Okay? Formal charge versus oxidation state, we'll address this just a little bit. Formal charge and oxidation state or oxidation number are different ways for accounting the electrons on each individual atom. Okay? Formal charge ends up being something that's a little bit more useful for us to manipulate because we can see how the reactivity changes. Because we can take an atom, say like, or one drawing where we had the sulfate with all of those oxygens be negative versus, versus neutral here, and we can see that there's now a difference in potential reactivity. The left one shows the oxygen is negative. We want to stabilize that negative. The right one shows the oxygen is neutral. There's no reactivity there, or less reactivity there. So formal charge allows us to predict something about that reactivity. Oxidation number, hopefully what you remember from Gen Chem, is that oxidation number is constant. Once you've assigned the oxidation number correctly, it doesn't change, which means when I go through and look at the oxidation number for each element in each of these drawings, it's the same. Well, how does that allow me to predict anything about reactivity if I have the same oxidation number? That's why we tend to not evaluate oxidation number, and we instead focus on formal charge. That's just that difference. I'm not stressed about you determining oxidation numbers, so you don't need to be able to quantify those. Formal charges you do need to be able to do. Okay? If you want to play around and look at oxidation numbers, that's fine. We can talk about that outside of class, but I don't want to deal with it right now in this video. Some Lewis examples. Let's take a look at CO2 because that's going to help us with this potential idea for best versus useful. So if we were to draw out CO2 and we followed our rule set, okay, hopefully we would be able to recognize carbon 4, oxygen. In fact, let's just go ahead and see if you can come up with the Lewis structures plural for CO2. For those of you wondering about that, maybe you should follow the method to see if you can find those structures plural. And now we'll go through and do it. Oxygen 6 times 2, we got 12 and 4, 16. Carbon, oxygen, place our electrons, 2, 4, 6, 8, 2, 4, 6, 8. Pair of electrons in between, we can turn into a line. We can check octets. When we look at the octets, that carbon has only 4, whereas our oxygens each have 8, which means we haven't satisfied octet, so we aren't good. So we need to move a pair of electrons in to make a double bond. Okay. Now we'd have 6 and still 8. That looks like an 8. Okay. So we would have to move another pair of electrons. Here's where that structures comes into play. How many of you drew that one? Everything still has 8 electrons. Everything is golden as far as our structure goes. So this structure is a valid structure. Okay. There are things behind the best and useful that come into play here, and we'll look at those in just a second. Okay. The structure you probably came up with would be something along these lines, where you had the double bonds on both sides. Okay. And arguably, we should have yet another structure with the triple bond out the other end, and we should end up with this for our final answers. Okay, so we should be showing all 3 of these, at least at the moment. Okay, and we'll address that at the moment in a second. So all 3 of those could potentially come out. So these 2, you might say, well, aren't those the same thing? You just flipped it over. When we're looking at resonance, our structures are pinned. Okay, and we'll address that pinning in another video. But our structure is not pinned, or is pinned, so we can't just flip it over. The triple bond is now aimed towards a different oxygen. One way we could do that or represent that a little bit differently is if we radio labeled that oxygen, we'd be looking at that oxygen being single bonded or triple bonded. So those are unique resonance structures of each other. Are all of these equivalent resonance structures? As in, should we be including these as all resonance for this? While they are valid resonance, are they the same energy? That energy has to do with the charge. And if we go through and evaluate charge, you'll notice that that is negative, that is positive, that is negative, that is positive. And in the one that you probably drew, which we'll go ahead and star, there's no charges shown. So if we're now going to consider something about, whoops, I drew the charges on that bottom one backwards. If we look at our structures now, we could evaluate difference in energy, and hopefully what we see is that that star one has no charge within it. That makes it the best. That's why you probably drew that one. You were reflexing to the best because that's what people showed. Why did people not show the other ones? Well, the other ones had charge and therefore are not the same energy as the best one, and therefore we shouldn't show them in the same sentence. Are they useful? Well, yes. That oxygen being negative means that I could now predict something about this molecule being reactive because I could put in a large positive to help polarize CO2, making that oxygen negative. For those people saying, well, couldn't I have done a large negative for this oxygen? Good, you're thinking along the right lines. But here's where that octet comes into play. Could I bring a large negative into that oxygen? Well, how many electrons are around that oxygen? 8. Because it is a very electronegative element, where are those electrons likely going, particularly in that double bond or triple bond? Those electrons are likely already shifting towards our oxygen, which means we'd be putting 10 electrons around the oxygen. So that negative wouldn't go there. It would go there. So having an understanding of where there are electrons and how those electrons disperse can help us predict something about the reactivity of these molecules. And sure enough, that second one with a negative, that reaction is taken advantage of in what is known as a Grignard reaction, and we can use that to make carboxylic acid functional groups. Okay? So if we have an idea of what is best versus useful, we can predict reactivity, and that's pretty phenomenally cool. But to get there, you have to understand the process that you went through to get those structures. If you don't understand that process, you're lucking into it, or you're guessing, or this is where you get the most common complaint for organic chemistry. You memorize. Oh, I had to memorize too much stuff. That's because you didn't spend the time learning the process behind it, and instead you shafted yourself and said you wanted to memorize everything. That's your choice. Right? And as long as we're clear on that, that's cool. Right? I suck at memorization. Look at the process. Okay? There are a bunch of examples listed here. You are welcome to go through and try those. We will be, or I will be, forcing you into some of them through our later slides. Okay? And I think we're not quite there. When you move through Lewis structure, what I want you to be doing is a lot of practice to get used to some of these patterns. So again, I want you to address or be aware of some of the simplifications. Remember, we're only concerned about limited elements. Okay? So we've got those limited elements there. The shapes and hybridizations we'll talk about in a little bit. We haven't gotten there quite yet. And we get to our drawings, those abbreviated drawings, we're going to start to see some patterns come out. If you're going to draw a large structure, say with a bunch of carbons in it, it's going to suck to draw all those C's. Okay? So that means we simplify our drawings. Every point is a carbon. Okay? So let's look at a quick example. H, 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 H. Okay, so there's a Lewis structure. Where are their points? Okay, well, a point is the end of every line. So point, 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 point. Okay, and here's where we need to be extra clear. How many carbons are represented here? This is where I'll get some people saying, well, there's 5, because there's 5 points. There are 5 points, unless otherwise drawn. These H's apply to those points, which means those points are H's, not C's. How many hydrogens are drawn or carbons are drawn? 1, right in the middle. That's a point. Okay, the molecule is now CH4. Okay, why do we do that? Because I don't want to have to draw the C's for every single one of those. And for those of you being like, the C wasn't a big deal there, okay, well then draw the formula for C10H20. Now it gets a little bit more complicated and you didn't want to have to draw all that out, okay? Which addresses the next issue. Because you might be like, well, there's only 10 carbons. There's 20 hydrogens. I don't have to draw every single hydrogens. Ta-da, rule 2. Hydrogens will be implied to carbon to satisfy an octet. Okay, so let's go through and draw that same CH4 molecule. You might be like, well, you didn't do anything. I did, I drew a point. Okay, that point is now by definition a carbon. Okay, since, and we'll look at the rule 3 and 4 here, since their charges are not allowed to be implied, okay, I know that carbon is neutral. Because I know the octet rule, I need to have 8 electrons around it. I know that there are 4 hydrogens also shown around it. Okay? So that information becomes embedded within this. So let's try another one. What formula did I just draw? Okay? So again, I'd look at my points. There are 2 points. Every line has a point. So I have C2. Now how many H's? Well, if we take a look, that line represents 2 electrons for that carbon on the left. Okay, it needs 8, which means there has to be 3 more bonds. Okay, for the carbon on the right, I need 3 more bonds, and we end up with C2H6. The amount of drawing we have to go through is dramatically reduced. Okay, and that's where this becomes helpful. Okay, so hydrogens will nearly always be implied to carbon, okay, to satisfy our octets. And there are cases when we're looking at our online homework where that isn't always the case and you need to specify them. The online homework will tell you, specify the hydrogens, follow the directions and you're fine. But this does kind of necessitate rule 3. Charges will never be implied. So if I drew out this, we might go through and say, well, this is C3, H, 1, 2, 3, 4, 5, 6, 7, 8, H8. But what if I wanted it to be C3, H7 with a negative charge? Okay, and actually I'm going to make it a positive charge. If I were to draw out that Lewis structure, there's going to be a variety of ways to draw this, but I would need to specify that positive charge. I can't just go through and say, well, that carbon is now positive. Okay? An implied hydrogen means it could have that hydrogen there. As soon as I put the positive charge on there, I now know that it only has 1 hydrogen. Okay, why? Well, if it's positive, it's missing its octet. Okay, it's going to have 2 electrons less than its octet, and there we go. There's our system. Okay, so never imply charges. Okay, and sometimes, well, actually, no, they're never implied and they're always shown. And the reason is that can help us understand implied hydrogens, and it can also help us understand if there's non-bonding electrons. So maybe we have a lone pair there. Rule 4 really isn't really a rule, but it's a bit unfortunate. Nitrogens, or everything within that column, are pnictogens. Oxygen, or chalcogens, everything in that column, and our halogens will very often have implied non-bonding electrons to satisfy the octet. I will try as much as I can in the first semester to never imply them and to always show them. Okay? But because they're almost always implied, it becomes challenging to remember to do that. And what you'll very often find is that they're just going to stop being shown. Because we're starting out OChem 1, you need that reinforcement of always showing those electrons. I'm going to try my best. Feel free to call me out, point it out in discussion posts, that kind of fun stuff. Okay. with that, we've addressed kind of our, again, basics of Lewis structure. If you went through this and were like, man, I don't remember any of these rules of Lewis structure, that's cool. There's a Lewis structure video specifically designed to really hammer home each of those points of Lewis structure. Okay? The point here is to practice, practice, practice your Lewis structure. Okay? Once you've got your Lewis structure nailed down, a lot of the patterns, like assuming carbons are points, will become second nature and it won't be a big deal. If you don't do the practice, it's always going to be a challenge. With that, I've talked way too long, and I'm fairly certain that was the last slide. So we're going to go ahead and end the video here. Thanks for listening.